Mysteries of the Cosmos. Proof of cosmic uncertainties far away. Spheroidal galaxies produce incredibly challenging questions regarding our modeling of the cosmos development process. Our problem is heightened because elliptical galaxies grew far away and long ago. As a result, the data that can reveal their arrangement is obscure. Nevertheless, there are mild relations between measured characteristics of the galaxies that comprise hidden aspects. One such relationship is the central plane of elliptical galaxies. This plane combines three measured amounts: the size, the expanse and velocities of the stars, and the mass of all the stars in the galaxy. A plot of those three measures and three dimensions reveals that they rest on a two-dimensional plane, indicating they are connected. Furthermore, how this came about is a puzzle. What is certain is that elliptical galaxies, as observed today, are very gently growing and evolving systems. Any association in their characteristics must have been marked at birth. Galaxies now are very gradually developing systems. These mounting relations must have been marked long ago when the galaxies constituted. The associations provide observational restrictions on how the stellar mass was compiled. We would sincerely like to differentiate our snapshots of the past inferred from the scaling relations with development models. However, unlike disk galaxies, we have no underlying hypothesis of spheroidal galaxy uncertainty and star configuration. Instead, there are phenomenological ideas that propose the notion that consolidations control the gas reservoir for creating stars. Consolidations without gas are called dry consolidations. A consolidation with gas is wet. A wet consolidation involves star development and leads to multiple alterations in morphology. Modeling consolidations tells us that dry or dry-ish significant consolidations indeed performed a vital role at a redshift of 1 or 2 in valuing for the morphological properties of huge ellipticals. One must also face gas-rich minor consolidations as the feeding source to break down the massive elliptical galaxy's unique objects. A minor merger means one in which the mass proportion is less than approximately 1 to 10. This needs to be one of the central routes for stimulating spheroid configuration. Mergers of gas-rich foundations supply the gas that settles the stars. Most importantly, the frenzy of the merger compresses and reveals the gas. As a result, the vapor falls into the interior region of the forming galaxy. Once sufficient mass in gas builds up, star formation originates in earnest. The creation timescale can be examined by analyzing the chemical characteristics of the stars. Elements like magnesium and oxygen are generated by massive stars supernovae. These stars only endure during the initial 100 million years of a galaxy's existence if there is no additional substantial gas injection. Thus, the magnesium in stars was amalgamated early in the galaxy's existence. However, components such as iron are also produced in supernovae, but regularly in supernovae, whose ancestors are long-lived low-mass stars. Numerous billions of years are thus needed to collect the mentioned iron in stars. Thus, the observed iron was manufactured late in the galaxy's development. The proportion of magnesium to iron in distant stars is an adequate archaeological timekeeper. It shows us how much time passed when these stars were being collected. The observed proportion in the Sun dictates the Sun to have produced about 4.6 billion years ago. A high ratio indicates that the stars accumulated over a much smaller timescale. In this way, we discover that vast elliptical galaxies must have developed within 100 million years. Disk galaxies, by contradiction, formed over numerous billion years. It so occurs that the breakdown time of a massive galaxy was about 100 million years. From this information, we gather those vast elliptical galaxies formed most of their stars monolithically through the primary collapse. Of course, the gas needs to have expanded for a while before reaching the stars. The intensification and the magnesium to iron proportion leave us with an astonishing conclusion. We had earlier thought that the larger the galaxy, the later it appeared, which is undoubtedly correct for dark halos. A result is that the later an object consolidates out of the expanding cosmos, the feebler the average density and the longer its initial breakdown time. That is the shortened theory, but in fact, we view the reverse. The data notifies us that the gas element forms stars much more swiftly on a timescale on the order of the dynamical time range of a massive galaxy. Not much star development could have occurred before when the gas was being constructed from many smaller objects, which hindered the gas from producing stars early before the heavy galaxy was in position. The event between star development time gathered from the chemical data and collapse time inferred from size and mass is adequately compelling to support monolithic collapse. Nevertheless, this poses the vital question of why monolithic collapse. We can argue that the beast in the center, the supermassive black hole in the heart of the galaxy, makes a distinction. Supermassive black holes are found at the cores of galactic spheroids, which are perceived as the energetic nuclei of galaxies. They accrete gas from their surroundings and are usually the reservoir of enormous outflows. If lesser mergers and accumulation collect the gas, some new component is required as a resolution. Thus, supermassive black holes could produce the missing link required to conjecture the mystery of elliptical galaxy configuration. The final determinant of whether a galaxy harbors a massive spheroid may rightly be the purpose of the galaxy's central working nucleus. The data for such a missing link originates from a discovery originally made by astronomer Dalton Morgan when he found a connection linking the supermassive black hole mass and the mass of the spheroid. The relationship only makes sense if both develop together at the same time. In the early cosmos, detailed measurements of a spheroid, velocity, dispersions, and black hole masses have presented articulate testimony to an informal relationship between active galactic nuclei and spheroid generation. We have noticed that star generation and disk galaxies are ineffective processes. Observe how useless it is. The specific timescale for star configuration, for example, is various gigayears for a galaxy such as the Milky Way. This is an order of magnitude larger than the orbital time, equivalent to the changing timescale. This slowing down of the evolutionary timekeeper results from what we call feedback from continuous star configuration. The feedback works on the gas that has still to form stars. Feedback works as follows. Stars form in a variety of sizes. The more extensive the star, the faster it develops. Stars of higher than about 10 solar masses decline spectacularly inside barely a few million years. Massive stars consume energy prodigiously and quickly exhaust their nuclear fuel stocks. The inevitable conclusion is that the core fails, releasing so much power so fast that the remainder of the star blasts. Radioactive wreckage is expelled. That decays into solid products such as iron, carbon, and oxygen. The hot wreckage is cleared up into an expanding shell that ultimately is stopped by the ambient interstellar force. The deceleration of the dense case by the thin interstellar gas is an unstable interplay. Claws of dense cold gas infiltrate the light warm gas. The shell cracks up and scatters. The enhanced debris from the bang emerges into the interstellar medium. The interstellar clouds are enhanced. The processing of gas towards stars is reduced because the supernova wreck also includes energy into the clouds. The cloud gas is stimulated. This is not the sole source of feedback. The revolution of the galaxy also mixes up the cloud movements. The galaxy rotates at a uniform velocity. When a cloud systematically wanders into an interior orbit, its speed increases related to neighboring clouds because angular momentum is conserved. A rock on the end of a spinning line has a more meaningful speed. When the line is reduced, these shearing changes also stimulate the clouds. The power source is the overall rotational energy of the galaxy. All of this is feedback. There is still feedback from developing stars. Magnetic lines of force wire the interstellar vapor. Clouds twist and turn up the fields as they close, and eventually the field boundaries snap. Magnetic energy is discharged into the vapor. Assembly of gas is reduced. Star configuration is delayed. A molecular cloud is extended up to an order of magnitude longer than the freefall time. The discovered gas means violent actions must manage the gas pressure cloud. Internal movements are perceived to be deeply supersonic. The fierce pressure counterbalances gravity since the disturbance is primarily motivated by stellar feedback. Cloud star development rates are self-regulating. Global self-regulation is dominated by the star formation time range and by the gas stocks. Star formation consumes the gas stocks. Dynamical intercommunications between stars and molecular clouds warm the young stellar disk sustenance of global disk vulnerability need a hard disk and the gas stores to sustain. This is implemented via gas accretion, which becomes about by constant fall from the halo and minor mergers. All these active communications, and therefore the gas disorder. The turbulence is shown in the cloud interior velocity structures. The supersonic disorder is thought to represent an essential role in accounting for the survival of star creation and disks. However, the global driving of the disorder, which usually would disappear on a small timescale, is not entirely realized. Numerical simulations of whole disks did not solve unique star formation, and stellar blast simulations have a problem following the turbulence's dissipation. The difficulty we have been considering concerning these galaxies presents an insight into how feedback in the universe works. There are some manageable analytic reflections. First, the low performance of disk star configuration lends itself to an outspoken interpretation of the gas section transformed into stars per disk revolution time. We have previously noted that this is recognized globally to be approximately 2%. Second, the section of original supernova energy free for stirring up the interstellar gas after enabling for radioactive losses is the proportion of the observed interstellar gas cloud speed diffusion to the velocity at which an expanding supernova relic has the impact of a snowplow and driving all before it. A relic expands initially at 20,000 kilometers per second. While it slows down by clearing up ambient gas to nearly 400 km per second, it efficiently transfers its momentum. The proportion of cloud motions to the velocity at which momentum is first adequately maintained happens to correspond with the recognized inefficiency of the gas exchange. This is not a shock. It is assumed that if supernovae indeed manage intense cloud velocities, supernova-driven droplets of hot gas, that sweep of cool gas into a compact shell presents us with a self-regulation basis for disk star configuration. The self-regulation is dominated by the interplay between the cold gas storage required for star formation and the contrary feedback connected with extensive stars, including their birth and destruction. One difficulty is that the disk is not a restricted environment. Supernova outbursts trigger the venting of disk gas into the halo. The gas cannot emerge from extensive disks. This is true for disks comparable in size to the Milky Way galaxy. The venting issues in galactic fountains. These galactic streams eventually cool and contribute to the store of cold gas that saves disk variability as a disk galaxy. The Milky Way galaxy is one of the best studied parts of star configuration history. There is a specific forecast for the content of the cosmos from the synthesis of the light elements. In the first 3 minutes of the Big Bang, we estimate the mass in interstellar gas and stars. Where are the baryons today? One opportunity is that the halo comprises compressed, massive baryonic halo objects called machos, for which there is at best limited evidence. Another chance is that most of the lost baryons are in the form of diffuse million-degree Kelvin gas. The remarkable dark matter hypothesis of structure configuration asserts that there is remaining addition of coal gas. The details of how the gas warms up on communicating with a halo are currently debated. However, the current gas content is expected to have increased the total baryon content over the past 10 billion years, indicating that a typical galaxy should contain 100 billion solar masses and distributed gas. This is an immense overvalue compared to what is observed. Observational restrictions expected that this gas must be ionized, otherwise we would have already viewed it. The gas procures high velocities when it comes into massive galaxies. It must agitate and heat up to almost 10 million degrees Kelvin. At this temperature, distributed gas glows in X-rays. X-ray views of nearby massive disks such as the Sombrero Galaxy detect only around 1 billion solar masses and hot gas in the growth area. The only explanation appears to be that supernova heat has forced most of the gas toward the exterior galaxy. This supernova warming produces winds, and certainly such superwinds are located throughout the Milky Way-type galaxies. This is confusing from a theoretical view because supernovae are deemed inadequate for driving a mighty wind from the gravitational potential well of a massive galaxy. Also, at least one instance is an extensive X-ray halo around a model, extensive spiral galaxy. In this case, gravitational increase and crash heating produce the most dependable source for warming the gas. The position for the Milky Way galaxy is complex because the local group, which is the regional aggregation of galaxies controlled by the Milky Way and the Andromeda Galaxy, presents a potential defense against the gas required. An illustration of the absence of halo gas in the Milky Way may rest in a complicated history, for the gas ejection plays a crucial role. One possibility is that large amounts of gas were dumped into the local group intergalactic medium. This could not have occurred recently, given the power of the Milky Way. Gravitational field dismissal, however, could have occurred long ago when our galaxy was raised from mergers of several smaller systems. Expulsion of gas must have occurred to some degree during the construction phase of the Milky Way. Winds were quickly forced from the star-forming dwarf galaxies that merged into the Milky Way. Some of those construction blocks reside in the halo as low-surface illumination fossil remains. To further confuse matters, we understand that the merging story of our galaxy itself included dwarfs that we are yet gas-rich. Star development and improvement transpired through the merging process. We understand this because the chemical bounties of the nearby dwarfs exhibit similar courses as the Milky Way halo stars, which suggests that a cosmic relationship endures between the wealth of elements such as magnesium and that of iron. There is one variation, however. The dwarf chemical abundances are frequently accounted to reduce metallic cores. Probably, then, dwarf composition happened earlier than disk and stellar halo configuration. Much of the increased gas eventually appeared. The disk of 50% could understandably have been discharged by supernova-driven winds from the dwarfs into the intergalactic medium in nearby dwarf starbursts. We indeed find that the wind mass expulsion rate is like the star production rate. More commonly, low-covering brightness dwarf galaxies are universal. Supernovae can remove much of the primary gas content. However, this gas must be deflected by growth. Otherwise, these systems would not lie on the perceived trend that correlates with completing stellar and gas mass to the rotation speed of the system, known as the Tully-Fisher relationship. Surprisingly, the low exterior brightness dwarfs are in the same relationship as more extensive disk counterparts on rich star-deprived dwarfs are imperceptible regarding the Tully-Fisher relationship from their gas pressure. This indicates that there must be a plot connecting stars to fair proportion and stellar surface density of the disk. Gravitational equilibrium demands that the previous should grow as the latter is degraded. One interpretation associates this link to a variation in star production efficiency induced by supernova feedback, although no model has been produced. Early-type galaxies control the luminous galaxies to the end of the light scattering of galaxies. It represents an exponential cutoff with a unique light of 30 billion solar luminosities in the accepted cold dark matter. Nearly 90% of the baryons are directly in the intergalactic medium. These baryons compose a large gas reserve probably open for recreation onto galaxies and ultimate star formation. Nevertheless, gas cooling and actual amounts of star development are not discerned for vast galaxies. Most are red and dead, and genuinely all star formation stopped a Hubble time ago. More commonly, it is thought that extensive spheroid development is discontinued by the forces of active galaxy outflows on the halo gas storage. Much of what arrives in must go back out. Outflows from active galaxies fall, removing the halo of gas, and directly relate to ancient and red ellipticals. There is a related gas cooling dilemma in galaxy clusters. Cluster galaxies are predominantly ellipticals, particularly in their hearts, but clusters are abundant of hot intergalactic gas that unavoidably cools in their cores. Gravitational collapse originally keeps the gas hot, but once the cluster forms, this heat supply is broken. Gas inescapably chills down once the heat source is switched off. According to speculation, the gas should fall into clumps that become galaxies, creating stars and becoming blue. Nonetheless, we do not see this occur. Something is presenting late heating and holding the cooling down. If delayed warming is expected in part to gravity, cold fall galaxies could not occur. These results may be sufficient to explain light quenching of a star formation by overcoming the cold gas supply. In contrast, active galaxy discharges provide temporary as well as moderate suppression of star production. There is a different way to solve light quenching. We can ask whether the various low lights, active galaxies we observe, might hinder cooling flows in galaxy groups. Somehow it must prevent the gas from building stars in large numbers. Low-light active galaxies may heat the gas but cannot be discharged via winds. Therefore, one presumes the halos of heavy galaxies to have a massive, scattered hot gas relative to the stellar mass. From an observational point of view, our thoughts of massive ellipticals show a baryonic shortfall within the halos of these gatherings. However, the baryons are unquestionably near group scales in intracluster stars and distributed gas. Moreover, the gas is enhanced, which gives an indispensable piece of data about its history. Enhancement of the gas by supernovae must have transpired. We understand this from this circumstantial evidence. Reasonable, the gas was expelled by vital supernova input, most likely in the beginning stages of galaxy development. In the state of the ellipticals, active galaxy outflows can provide the energy source. Nevertheless, these are unavoidably connected with robust star production activity, perceptions of ultraluminous infrared galaxies. The brightest galaxies in the cosmos indicate winds in these galaxies. Most of the stellar mass has now been gathered. Nevertheless, they have light above 100 of our Milky Way galaxy.
Jai Mamari Nina Tuda Laraba Kopana Lana Tula Bahang